Hi everyone, welcome. In this video, we're going to discuss about graphical interpretation of integration of a function. Over here, we have two panels. On the top, you have integration of f of x with the limits from 0 to x, meaning this is a definite integration we are looking at. In fact, most of the times in physics, we'll be dealing with definite integration. Only in two cases where we calculate potential energy and potential, we'll be using indefinite integration. Except these two cases, any other situation if you consider, we'll be generally taking definite integration. So the definite integration has got a meaning here, which is area under the graph. Integration represents area under the graph. That's a basic understanding, central idea that we would like to bring it on to in this particular simulation video. So at the bottom you have f of x, which can be plotted with these four commands that we have here. We can have curved graph, up and down, and then we also can have a rectangular graph, flat curves, and then these graphs can be rotated anti-clockwise or clockwise. And also we have fourth command, which is to slide the graphs up and down, not rotating but sliding. So these are the four commands we have. Using these four commands, we can plot f of x, the blue curve. Depending on the f of x, the simulator will automatically give you that area under the graph, that is a green curve, which is integration. The integration represents area under the curve. Let me show that area also on the left hand side to understand that. We have this green dot to indicate the area. Wherever I keep, that is the upper limit we have here. So we can also show that in grid lines so that we can measure the areas also. So let us start with the easiest one. First, let us take the straight line graph, which is parallel to x-axis at a height 1 unit. Now this is x coordinate. We have x equal to 0, upper limit 0, lower limit 0. 0 to 0 will be area 0. But suppose I go for x is equal to 1 unit. 1 unit if I go to, now it is going to cover 1 square unit. Area of this will be equal to 1 unit width and 1 unit height, 1 square unit. So that is going to be shown here as a green height. And you can also see that integral 0 to x equal to 1 here, f of x would be equal to 1. You see it is going to be exactly 1. Now if I make x equal to 2 units, that means x coordinate has become 0, 1 and then 2 units. So now you look at this rectangle. This rectangle has got a base length 2 units and the height has become 1 unit only. Height is not changing here. Whenever the graph is parallel to x-axis, the height wouldn't change. The base is 2 units now, height is 1 unit, and that's why you have two areas. You see 1 square unit and then second square unit. Total area under this graph would be 2 square units, and that is what you get here. Of course, you cannot see that in a quantitative manner, but definitely you see it has become more now. And now you look at the unit here, 1 and then 2 units. It is showing 2 units here. Likewise, we can go on further. When I go for 3 units base, x is equal to 3. Height is 1 unit only. 1, 2, 3. 3 square boxes are covered. That means the area under the graph now from 0 to x equal to 3 is going to be a rectangle area which is equal to 3 square units. And you see the height has increased. And here f of x integration is 1 unit, 2 unit, 3 units. That's the area you have it. And you can go on further. 4x is equal to 4, area becomes 4 units. You can reduce the scaling further down if you want to. And when you put x is equal to 5 units, you see that the area becomes 5 times 1 and then 2, 3, 4 and then 5 units and so on. So now you see that the area is proportional to x there. You will see a straight line passing through origin. Okay, that is one simple graph that we have here. What if we have the same straight line graph not above x-axis but below x-axis? Whenever you have below x-axis, you see it is going to be a dark green color area. Above x-axis, it is mild green color area. Whenever it is below x-axis, we see that y coordinate would be negative, x coordinate is anyway positive. So the area that you take here is taken to be a negative area. And you see that negative area is shown in negative direction. You see here the quantity is f of x dx integration from 0 to x has become negative value. 1 unit, 2 unit, 3 unit, 4 unit, 5 units only. So the same amount of magnitude, but now it has become negative. When you take it up, area would be positive area. When you take it below the x-axis, it is going to be negative area. What if it is not parallel to x-axis? If I turn it to some angle, let's say I'll make it like this, exactly 45 degrees line, I'll make it. You see here, when x is equal to 1, y equal to 1. When x equal to 2, y equal to 2. Y equal to x graph I'm considering for this simplicity sake. Let us take this area, for example, from 0 to x equal to 1. This area, if you consider, now it has become a right angle triangle area. For a right angle triangle, area would be half into base into height. Half into base is 1 unit, height is 1 unit. Half into 1 into 1 will give you half a unit. And you see this is a square box, and that half the area is under the graph, between x-axis and the graph. So the area of this will be half unit, and that is what you see, half unit. It is not 1. It is between 1 and 0, the y coordinate of this particular function, which is integral 0 to x f of x dx. X is equal to 1 here. That is going to be the area you get there. Now you make x equal to 2. When you make x equal to 2, what is happening is the base has become double, even the height has become double. And so the area becomes 4 times. 2 into 2, 4 times you will have it. Earlier you had this half a box. Now you got this extra 1 box and then half a box. So half plus half 1 plus 1. Totally you have 2 square units of the boxes under the graph and of course above x-axis. So now area has become 2 square units, and you see the graph, and upper panel will show you 2 units, 0 to 1 and then 1 to 2. 2 units you have it. So when x becomes double, area becomes 4 times. Because the variation is much rapid for the upper graph, it won't be a linear graph. It would be a curved linear graph. In fact, it will be a parabola. Now you can go on further. When x equal to 3, y would also become 3 and area becomes 9 times. 9 times the initial value. Initially half you have. 9 times the initial value will be 4.5 times. 1, this is 1, 2, 3, 4 and 5 years over there. In between you have it, 4.5 units will be that integration from 0 to x when x equal to 3 units. 0 to 3 f of x dx would be equal to 4.5 units. Anyway, integration is area under the graph, and that is the point we are trying to bring to your notice here. Alright, now suppose the graph is downward sloping. You see that the graph would be the same, just it will get reflected down. You imagine a mirror on x-axis. Whatever graph you had earlier, it gets reflected down. So whenever you have the graph upward sloping, you have the area is positive, f of x will be positive. Whenever it is downward sloping, f of x will become negative, it gets inverted. And you can also have a graph which is being translated as well. You might have a graph going like this. Now you see, as x is varying from 0, alright, area is increasing. It's a trapezium area that you will get. For the trapezium, the base is increasing. So the trapezium area is going to keep on increasing. Area increases, but the increase will be lesser and lesser. That's why it is going to be a concave downward graph you have here. And as you move further and further, up to x equal to this much, you see that area will be keep on increasing because it's a positive area. You're adding positive values now. If you want to count it right now, approximately, so this is one box. This is slightly less than one box. If you add this tiny area over here, approximately it looks like matching. So this plus this together is one box. 1 plus 1, 2 square units. And then this one, probably if you add it to this, if you take this to here, looks like it is going to approximately match. If you count it that way, it will be approximately how much? One box here, two, these two together, and then these two together, three. 3 units must be the answer. Is it the answer? We can count it from 0 to 1, 1 to 2, and 2 to 3. 3 units is the area that we get it. So we can approximately measure it that way also. But then as you go further, as x is increased further, now you see that negative area starts increasing. Up to that it was positive area increasing. Now the negative area increasing. So positive value is added to the negative value. You see that the value overall is going to decrease now. When you come to here, for example, this particular area, this triangle which is a positive area, is exactly nullified by this area. These two look like almost the same. So this plus this together would be 0 area. Then the leftover area would be this and this 1, and then 2, 2 plus slightly less than 3. 2 and 3 in between, probably 2.75. Yes, 1 and 2, 2.75, 2.7 in that range. But anyway, you understand that earlier you had positive area, now we are increasing, but that is going to be negative area. As the negative area increases, overall area will be keep on decreasing and decreasing and decreasing. There will be a point where area becomes 0. What it means to say is that this light green area, which is positive area, is exactly cancelled by this dark green area, which is negative. So this plus this together has become 0 over there. Beyond that, the negative area dominates. But anyway, you see that the graph is again curvilinear. It's actually going to be a parabola. Whenever you have a linear graph, its integration would be a parabola that comes qualitative also. We can analyze it. Now let us rotate it up. You can see this kind of a graph you have. See, initially, as you start from x equal to 0, area would be 0. As you keep moving, you see that y coordinate is negative up to this point. So up to this point, area would be negative and increasing. Beyond that, area would still be negative because positive area is added. As positive area gets added and added, it will be a point where the total area becomes 0. So at this point, we can say that this dark green area is exactly cancelled by this light green area. Dark green area indicates negative area because it's below x-axis. This is positive area, net will be 0 here. Beyond that, the positive area dominates and you have positive area going upwards like that. Okay, then this is the linear graph. When you go for curvilinear graphs, it will become much difficult. So in that situations, we'll have to go with qualitative analysis. So maybe let's say we have a graph, something like this. Now let us look at the area under the curve. Initially, area would be 0 because it was coinciding with the x-axis. Up to here, area would be 0. F of x integration will be 0 only. But beyond that, you see that area is becoming dark green, which means that area has become negative. And it kept on increasing, that green area is increasing. Up to here, green area increases. And after that, area becomes constant. There is no more area added. So in here, you see that integration function has become constant. Whenever the function is 0, integration becomes constant. How about moving it up like this? Let us say I move it like this. Maybe something like that, I'll move it. Now you see here, initially you have 0 area. Then after that, it became negative area. You see the integration function is going down and it increased like that, kept on increasing up to here. This is where you will have the maximum amount of negative area. After that, positive area starts adding up. As positive area starts adding up, net area will be keep on decreasing and decreasing and decreasing. And you see, I gave the graph in such a way that at this point, whatever negative area you had up to this point is exactly cancelled by the positive area after coming here. So beyond that, net area would be 0, and you see that integration of the function will become 0 there. You can play around with it like very nicely. So you can move it up and down. You see how the area of the graph keeps on changing. You can see the shades of it. The point here is that very simple, that area under the graph represents definite integration. Thank you very much for watching. Until next time, goodbye.